So when you draw your orientation, make sure your deformation is either smiling face or sad face. Okay, make sure your deformation, the smiling face, is sad face. It cannot be into the page. Okay, if not, you cannot apply. You cannot apply what? This is compression. This is tensile. Okay, you cannot apply that now. Okay, so now you know. So I'm going to call this our point I. Not point I. We're still, yeah, it cannot be the same name. So this is our point I. Over here, this is our point J. Okay, there's a point. So the formula we're going to apply is still stress in the x direction. Now is moment about y over I, y multiplied by z. Okay, so we know the moment, right? As what we had before. We know the moment about y is equal to 60 Newton meter. Now the z max and mean is equal to what? So if you look at the y in the z direction, 12 millimeters divided by 2, so it's plus or minus 6 times 10 to the power minus 3 meters. Okay, so once you have this, it's easy. Not easy. So next, okay, is your IYY. Okay, so I'm going to draw the structure in the same orientation, the cross-sectional view. So this is our Y, this is our Z, and this is now our rotation about X. Okay. So now we want to find, is it the same? Yeah. Excuse me. Now we want to find YY. So YY axis. So now you construct your YY axis. Okay. So this is your YY, right? So when that's the case, this direction now, parallel to the axis of interest, this is your width, and over here now, this is your depth. And based on geometry that we have drawn or we are given, this is your 12 millimeters, the distance from here to here. This is your 20 millimeters. Okay, so when this is the case, I YY is equal to width depth cube over 12. So now your width is 20, your depth is 12 cube over 12. Okay, so 20 times 12 power 3 divided by 12 is equal to 2.88 times 10 to the power 3 millimeter 4, or 2.88 times 10 to the power minus 9 meter 4. Okay. So when this is the case, now we can calculate our stress. Still stress in the x direction at point I, right? So moment is still 60. We found IYY is 2.88 times 10 to the power minus 9. The distance is 6 millimeters. And we know at point I, we've just drawn is in compression by looking at the moment vector. So this is minus. Okay. So this is equal to 60 times 6 power minus 3 divided 2.88 power minus 9 is equal to 125 or minus 125 times 10 to the power 6 Pascal. So likewise, stress in the x direction at point J is in tensile, same thing. Now it's only in tensile mode. So it's got positive 125 times 10 to the power 6 Pascal. Okay, so you realize that whether is it moment about X or moment about Z or Y, right? Your stresses are still in the what? X direction. Okay, so now let's sketch what is going on. So I'm going to put this. I'm not going to change the orientation of the beam. I'll put the beam orientation still the same. But I do need more space, so probably I will come on. I will push it over here. Okay. So now we know that over here now our normal stress is still in the x direction. Okay, so I'm still going to draw our normal stress. Okay, so this is our normal stress in the x direction. And then the next one is our next axis is our z. Right? So this is our z. Okay? Okay. So we label this as so over here this is our point wait, how did I label this? Okay, so this is our point I. Over here this is our point J, right? So J is positive, I is negative, so the orientation will look this way. Okay. So over here, this is our 125 megapascal, and down here is our minus 125. Okay, so to sketch our stress field distribution, so this is compression, is pushing towards, and then this is our tension pulling away. Okay, so this is our stress distribution. Okay, still stress in the what? X direction. Okay, again, the exercise over here is to emphasize this formula. Okay, is to emphasize. So when the moment is in Z, you use IZZ. When the moment is in Y, use IYY, and you need to view in the right orientation, then you can determine what is compression and tension. Okay. Oh, I have one question, sorry. Top view, yeah, top view. Hon Chong Cheng, you're right. Okay. Okay, we are going to do another example. Okay, we're going to do example. Wait, yeah, we're going to do example 2. Okay. So again, you can get this diagram. Over here. Okay. So 2 vertical forces are applied to the beam of the cross section shown. Determine the maximum tensile and compressive stress in portion BC of the beam. Right. So this is where we are going to practice our cantilever. Let me elaborate later on what do I mean by let's practice our cantilever. Okay, so this is our example number 2. So where this structure will fail is this structure will fail at the center. Okay, this structure is going to fail at the center. Okay, so I'm going to draw our transformation first. Okay, we're going to do our transformation first. And for this example, we can also sketch our normal stress distribution. Okay, let's also sketch our normal stress distribution. Okay, and as you can see, this is typical problem where it's symmetrical centric loading. Okay, so first we construct our transformation. So this is X, and this is Y, and this is our rotation about Z. And over here, what you see is our cross-sectional view. So this is our cross-sectional view. The transformation is like this. Okay. So this is our Y, and this is Z. So if we were to look at how the structure will deform, the structure will deform in this direction. Right? So to deform in direction, you need moment acting in this way. Right? So now you already know which is the tension and which is the compression. Okay. So you know that this is on top is our compression. So this is our moment in Z direction. All right, we know that already. So this is compression. And over here is tensile or tension. And then we know that the formula we're going to apply is going to be stress in the X direction is equal to mz. Now we know mz is over izz, yes or no, multiplied by y. Right. So once you know all this information, right, you know that, okay, so we are interested in moment about zz. Okay, zz. Now we have to find what is our y bar. Okay, so this is our what? This is our centroid. Right? So we know that there's our ZZ. So immediately write down this direction is your width. This direction over here is your what? It's your depth. Okay. And this is what we call analysis. Okay. This is all the analysis that you need to carry out. Okay. For you to do this problem. Right. So it's everything we learned today all done in a figure. Right. Right, everything we have learned today regarding the width and the depth, looking at the moment, what is a compression, tensile, and we know now. If I were to tell you this is symmetrical bending, you know why? Because whatever occur over here will be the same on the right hand side, right? Because the equation is only as a function of y. Okay, that's why we call it symmetrical loading. Okay, so from here. The problem is the question says between point B and point C. Okay, so we know if we're going to do anything to the structure, where your break is your break at the center. Yes or no? Failure is going to be at the center. Okay, for this case. Okay, so now once you know that, okay, so you are saying you call this point E. Okay, so you are going to find the moment at point E. Okay, we have to find the moment. So we're going to construct our free body diagram. Right, we're going to construct our free body diagram. So we know for a fact that AY and this is our DY, and over here this is 10 kilonewton. Over here this is 10 kilonewton. Okay, so point A, point B, point C, and point D. Right, so you can just write this out. Okay, so we know, okay, we can just write this out again. I'll put down my transformation X, Y, and rotation about Z. So you can write that based on symmetrical loading and geometry. Okay, AY is equal to dy. Okay, so when that's the case, positive is going up, summation of forces in the y direction is equal to 0. So it's equal to AY minus by 10 times 10 to the power 3 minus by 10 times 10 to the power 3 minus by or plus by dy. So thing equal to 0. Because AY is equal to dy, you can write A 2AY is equal to 20 times 10 to the power 3. AY is equal to 10 times 10 to the power 3 Newton meter. Okay, you can write that out. If not, okay, if you don't write that out, okay, if you don't know, you can also take, I'm going to show alternate method number 2. Okay, we're unsure, it's just a bit longer, it's fine as long as you are comfortable. You can take your moment in the z, right? I'm going to take moment about point A is equal to 0. Okay, so the 10 kilonewton is going to be clockwise minus 10 times 10 to the power 3, and the distance I'm going to see down here, the distance is what, 0.15, right? And then again minus 10 times 10 to the power 3. Now the distance is 0.15, so it's 0.4. Okay, plus by, okay, dy is going to induce